Can you turn on both knobs to the top position? Extra louder. The white point to the top. 12 o'clock position. 12 o'clock position. Accelerometer can be used to measure angle. So this lecture is going to introduce you how to use accelerometer to measure angle. So this one, AD-Accel203, is an accelerometer. But we use 7887, this one, it's a converter to convert analog signal to digital signal output. So AD787 is a SAR ADC. SAR ADC, so it's your ADC. And for this accelerometer, is two-axis accelerometer. It can measure two-direction accelerations, x-axis and y-axis. So this accelerometer has x-axis output, y-axis output. Then we need a buffer. This is the buffer, because the output range of the sensor does not match the input range of the analog digital converter. So we need a buffer to convert the output of the accelerometer to the input range of the analog digital converter. So that's the purpose of this buffer. AD8608. Quad means 4. We have 1, 2, 3, 4. We have 4 amplifiers inside, up amp inside this AD8608. So now suppose the output from X out, Y out, we have a range. Then first stage, we shift the output range. We have a new range. Second stage, we shift the range to meet the input range of this AD converter. So AD8608, it has low offset voltage, low bias current, and low noise, small footprint. So it has all the advantages we need. Okay, so this is the introduction of the circuit. Then remember supply voltage to this accelerometer. What is the purpose of the capacitors here? Why do we need the capacitors here? Okay, to remove the high frequency AC signal, because we just need the DC signal. Because power supply, we only need DC. We don't want AC power inside to get into the power supply. Okay, so we have two capacitors to remove the AC noise. Then another important thing is the bandwidth. Bandwidth is frequency. So large bandwidth means high frequency, and high frequency means speed, quick response. So if we lower the frequency, the response time is going to be longer. So there's a trade-off, response time and frequency, bandwidth. So we need to set the frequency range for our sensor. So frequency R and C combination is the frequency we can set. Then we have CXY. So this is X output. So we have, this is CX. We add this capacitor here, and this one, Y out. So this is CY. And we have output resistance. Output resistance. So R and C combination. We create a filter, RC filter. So the bandwidth is 1 divided by RC is the frequency. So CXCY, Army, what is the purpose of CX and CY? Alvan, tell him. So okay, so this is the equation to calculate the frequency. Let's see, low pass filter. The 30K ohm. So for this accelerometer, this sensor, the output resistance is 32K ohm. Then the bandwidth equal 1 over RC. But we want to see frequency, so you divide it by 2 pi. 1 divided by 2 pi RC is the bandwidth unit, hertz, Hz. So this is the bandwidth, 3 dB frequency bandwidth. Okay. Then, Ami, I love you today. So why we use 2 pi here?
See the frequency.
Why? Why? Muslim.
Is the total angle.
I don't like the answer too, either. So, again, why I divided by 2 pi? Why? Kind of.
Because we want frequency.
Because what?
Frequency.
Yeah, it's frequency, but why? 1 over RC is frequency, but y over 2 pi RC is also a frequency. So why 2 pi? What? No one knows.
Maybe 2 pi represents load.
It's about unit. Leo.
You know, hertz, we change the unit to hertz.
Yes, from radian to hertz. RAD. Because 1 hertz equal to 2 pi RAD. Okay. Then the roll off because this one is a low pass filter. So if you look at the frequency response, we have some gain, but after this frequency, the gain drops. So we call this roll off. Like a ball rolls down along a hill. So roll off. So this is a single pole. Okay, roll off characteristic. Then, but any sensor, we have noise. The noise comes from temperature. The noise comes from the circuit on off. The noise comes from mechanical reason, vibration. Well, anyway, we have noise. Noise from circuit, noise from temperature. So we have this spec, RMS noise. So it's 110 micro G, because this is unit of acceleration, divided by square root hertz. So this is noise density, but the noise, when you calculate noise, so this is the density, you need to calculate times by, we want to know what's the noise in terms of G. So we have unit, micro G divided by square root Hz. So you need to multiply by square root Hz. Then square root Hz can be cancelled out. So we can get the true noise in terms of your, so you calculate the bandwidth, but you have this parameter. So we don't care how the analog devices, the company, the engineer, usually we don't need this one, but they include this one here, means those engineers, when they do the math, they figured they need to put this parameter here. Okay, so this is RMS noise. Kyler, what is RMS? RMS.
Root means square.
Okay, root means square. Then exercise for you. So we have the bandwidth. We have the 4 numbers here, and we have the CXCY for you. So case 1, bandwidth 10 Hz, CXCY 0.47. So please calculate RMS noise. Use the equation in the previous page. So we have 4 numbers to calculate, and we have 8 students. So you two calculate the first row, you two the second row, you two the third row, 1, 2, 3, and you, the 4 students here, please calculate the final row. So I give you this number and this number. Please use the equation to calculate this number. Okay, start please. The hand calculation. Then for this accelerometer, the material is polysilicon. Then we use a differential capacitor to detect the output. Remember, we have 2 fixed electrodes and 1 moving electrode. So the moving electrode moves between the 2 fixed electrodes. We will have C1 decrease, C2 increase, or C2 increase, C1 decrease. So we use this differential capacitance to get the voltage output. So you have calculated this one, differential output, in your homework. And for C1 and C2 to work, we need to have signal, the carrier signal. So the carrier signal is 180 degrees out of phase, means one positive, the other one negative. C1, C2, and 2 power supply. VS1, VS2. So one is ground to +5, the other one is ground to -5. So they are 180 degrees out of phase. Okay, they use out of phase square waves. Okay, then, okay, so this is the top view of the ADXL 203 accelerometer. So just imagine if you, so this is X, this is Y. So in this way, we can measure X output -1G. So if you rotate 180 degrees, we can get X out 1G. And this orientation, Y out plus 1G, Y out minus 1G. And if you put it this way, then there's no output. X out, Y out are 0G. So, okay, this is the Earth. So, this way, this way, this way, this way. If you put it this way, like this, then there's no X and Y accelerations. Then, if it's 0G, we have the bias 2.5 volt output. Then if you, the sensitivity of this sensor is per G, we have 1000 millivolt output. So this is the sensitivity. This is total sensitivity of the device. Remember, we did some lectures about total sensitivity equal to mechanical sensitivity multiplied by electrical sensitivity. And mechanical sensitivity in this case is Faraday divided by acceleration. Then electrical sensitivity is volt divided by Faraday. So Faraday divided by G times volt divided by Faraday. Faraday cancel out. So the output is volt divided by G. So this is volt divided by G is the total sensitivity. But they prefer millivolt as the output unit. So 1000 millivolt per G. So, okay, in this case, you can calculate if 0G is 2.5 volt output, then if in 1G field, see 1G we have 1000 millivolt. 1000 millivolt is 1 volt. So plus 1G we have 2.5 volt plus 1 volt. So total is 3.5 volt output. Minus 1G, see minus 1G. This one times minus 1G. G cancel out. Minus this one. So equal to minus 1V. So 2.5 minus 1V equal to 1.5 V. So this is the output between 1.5 volt and 3.5 volt. So any question? But the signal conditioning, we have something inside the circuit. So your output won't be 3.5 and 2.5. Something happened inside the circuit. So because we have the buffer, and we have the ADC, the converter. So then we need to calculate what happened. Okay. So AD7887 for this IC, the input range is from 0 to 3.3 volts. So this is the rule. We bought this IC, then we need to follow their spec. But the ADXL203 output range is 1.5 to 3.5. So they do not match with each other. So that's why we need to design a buffer between them. So this is one problem. We have other problems. The 0G bias level. The perfect world is 2.5 G, but we have done something wrong. Something just caused the output. The 0G bias could be 0.4 volt. It could be 2.6 volt. So then the second problem is the sensitivity. Although the perfect world sensitivity is 1000 millivolt per G, but it won't be that way. Because fabrication, the mechanical device, we have geometry, we have dimension problem. You design your device to be 10 micrometers thick, but in reality it might be 9.6 micrometer. So mechanical error. Also, we have temperature problem. Then, so yeah, the output could be 1040 millivolt per G or 960 millivolt per G. So we have some problems. Then we have some simple calculations here. Worst case output means the possible maximum and the possible minimum. Consider all the cases. The worst case scenario. For plus 1G, see what's the maximum output possible. Because remember, bias, 0G bias 2.5 volt, but it could be 2.6. So maximum possible 2.6. Then you want to reach the maximum, so you need to use this number as the sensitivity. If you use this number, you cannot reach the maximum possible voltage. So 1040 mV per G times 1G, so you can get 3.64 volt. The maximum possible number you can reach. And the minimum possible number you can reach 2.4 volt, the 0G bias. Then you use this number times minus 1. If you use 960, you're not going to reach the possible minimum value. Okay, so this is the possible minimum value. Kaiser, do you understand? Why didn't I use 960 mV per G here? Why?
Because in that case we will not get to maximum voltage.
Okay. So now the ideal is 1.5 volt to 3.5 volt, but the worst case scenario is 1.36 to 3.64 volt. Okay? Then this is the maximum value, this is the minimum value. What's the common mode value? You just V maximum plus V minimum divided by 2 is the common mode. So the common mode is 2.5 volt. So that's why we get this 1.36 volt to 3.64 volt. and the VCM common mode voltage 2.5 volt. So this is the input. So now it's your job to do the calculation. So these two resistors is the gain, set the gain for this OP. And this 5 volt will determine the common mode output. So try to figure out from this stage to this stage why we got minimum, maximum, and the common mode. From this stage to this stage why we got minimum, maximum, and the common mode value. Okay, you can discuss with each other. Start. You can ask someone else. Just try to figure it out. So remember, when you do the gain calculation, so this is, so the input to this non-inverting input of this op amp. So common mode 2.5. So the maximum value here, so you need to do this one, because the gain amplify differential, not absolute value. Remember, for op amp, we amplify the difference, differential value. So this is 5K, 1K. So for differential input, Vx. So Vx in here, also Vx. So Vx, and this is V out. So Vx equal to V out times 5K plus 1K. Then the denominator is 5K. So 5 divided by 6. So you do reciprocal. So it's 1.2 is the gain. So the differential gain, so this is the differential output. And this is 2.5. So this is the minimum value. The maximum value minus this common mode times the gain. This is the output, but you need to calculate the common mode. So for common mode 2.5, 2.5 here means here is also 2.5. So here is 2.5. 5 volt here, 2.5, 5. You have 1K, 5K. So you know how to calculate the common mode, this point. I mean, do you understand? Okay, so this is VCM minus 2.5. Divided by 1K. So VCM here, VCM minus 2.5 divided by 1K equal to 2.5 divided by 5 divided by 5K. Because current goes this way, goes to 5 volt. No current going through the op amp. So current. So this is current here, current here. Okay, so VCM equal to 2 volt. If you know VCM is 2 volt, so this is the maximum value is common mode plus this one. And minimum value is common mode minus this one. So that's why we get 3.37, 0.63. So you can apply the same logic to get the output here. So remember now 0.2, good, is higher than 0. And 3.2, good, is lower than 3.3. So we shift the output of the accelerometer to meet the input of this ADC converter. And the headroom, see 3.2, the distance from 3.2 to 3.3, we have 1 millivolt headroom. And to the bottom, ground, we have 0.2 volt. So the headroom here is 0.2 0.2 volt, 0.1 volt to the top. So we are quite safe here. So this is the mass to calculate the second stage. So headroom means the gap. So the headroom to the top, 200 millivolt. And the headroom to the negative end, the ground, is 100 millivolts. Okay, so this is the buffer stage. Now, in the beginning of this lecture, I tell you how to use this accelerometer to measure the angle orientation. So this is the way we could do it. Suppose this is the accelerometer, this is the gravity, 1g, the Earth's gravity. What is 1g? Okay. Do you need to wash your face? Go. So let's take 10-minute break. We'll come back here around 2:40. Okay, this is the accelerometer, x-axis. So now we rotate the accelerometer by angle theta. But the gravity the same. I rotate this way, gravity this way. I stand this way, gravity this way. Doesn't matter. So now I want to measure the angle theta. Okay, so remember we have the AX output from the accelerometer. But now the acceleration, so this is G, so this is angle theta. So G here, you can plot this angle theta. So 90 degree, 90 degree. So this angle is theta. So in this direction, we can separate this G into this component and this component. So this component is 1G times sine theta. 1G times sine theta is now the acceleration measurement, AX. So we can do the inverse. So theta equal to arcsine AX divided by 1G. So this is the method to calculate angle using accelerometer. Okay, so now let's look at this figure. The x-coordinate represent angle theta. The y-coordinate represent the output acceleration, AX out. So in this figure, you can get this output. Then if theta is 0, then the output is 0. Because theta 0, output in this way is 0. But you plot this one, when the angle nearly 90, 80, 90. Now the sensitivity. So output versus angle is the sensitivity. So nearly 90 degree and minus 90 degree, the sensitivity drops. Although we prefer this way, linear sensitivity. So this is nonlinear. Nonlinear. So, but AD02365. Okay, this accelerometer, we have two axes output, not only one axis. So we can take advantage of the two axis output. Now again, X and Y, this is G. We rotate angle theta. So now AX output is 1G sine theta, but AY is 1G cosine theta. Okay, so you can use this equation to get this one. use this equation to get this one. But we can combine these two. Sine, cosine become tangent theta. So AX out divided by AY out equal to tangent theta. And theta equal to arctangent AX out divided by AY out. So we plot the sensitivity again. The x coordinate represents angle. The y coordinate represents the output. So x-axis output is the blue line. Y-axis output is the green line. So we combine these two together. You can plot this one, tangent theta, arctangent. So this plot only show you arcsine, arccosine, no arctangent. But you can plot this one by yourself. So now the time is 2:45. So please, I will. Okay, line, come here. So plot this one, then another red line with arctangent. Use method. Method ASIN is arcsine, ACOS is arccosine, ATAN is arctangent function. So three function versus angle. Okay, camera off, please. Okay, but there's always an error in our measurement. So the error could be offset error or sensitivity mismatch error. Like what we said, sensitivity is not 1000 millivolts per G. We have some variations. And we have the offset because for any system, we have input bias current, and we have mismatch in the input resistance. So the input resistance multiplied by the input bias current, we can get input bias voltage. And yeah, this is the offset. Then the offset will go to the output, even without any acceleration. Due to the input offset voltage, you will have output. So we need to calibrate this value out. So calibration is important before your experiment. Every time before you measure your result, do the calibration. Otherwise, your result is wrong, not correct. Okay, so how to do the calibration? Remember, even without actual acceleration, you have the offset output go to the output. So we need to remove this term before we do the measurement. The input offset. Okay, so yeah, we know gravity is 1G. So you do, so the simple calibration method, you just put the axis in a 1G, along the 1G, your result should be 1G. If your result is not 1G, then that's the offset. the simple calibration. Then you can do 1G calibration, then rotate 180 degrees, you get minus 1G calibration. So, okay, 1G output here, minus 1G output here. Then you have two equations. Then this one plus this one. Cancel out. So 2 times A of equal to A plus G plus A minus G. You move 2 here, you have 0.5. So using this two term, this one and this one, you can get offset, and also you can get gain. One variable, two variable, two equations. Then you can get the gain of your device and the offset of your device. So we have one turn method, two turns method. You can use multiple turn method. You can turn this way, a lot of ways. Then you can use this. You can get very correct calibration. Yeah, it's just multiple turns to do it. So this is multiple turn. You can rotate 360 degrees. You can get a lot of data in 1 degree increment. Okay, you can do this. Input angle, then output angle error. Also, like PCB board is always, although you do SPICE simulation, you can get very beautiful output. But when you put your components to the PCB board, then probably maybe you won't have any result, or your result is meaningless. So PCB layout is crucial. So look, there are several things you can pick up, because you are not going to consider everything. So after you become a very experienced PCB designer, you know what to do, but it may take 2 years, 3 years, 5 years. So when you learn, you read something, you pick up some knowledge, and someday with some mentor, maybe when he tell you what to do, then you may connect his teaching to what you learned in the past. Then it makes sense. Like in your circuit, you have digital circuit, you have analog circuit. You need to separate them as far as possible. So this is one thing. Then PCB board, the large ground plane, and power supply and ground return layout on the board. So, okay. Here, DC bias, this one, 0.1 microfarad, 10 microfarad for the DC bias. Also here, 0.1 microfarad, 10 microfarad. So that is important. We remove noise, AC noise, reduce ripple. Then the capacitors, this one and this one, should be placed as close to the device as possible. They cannot be too far away. They need to be very close to your device. ceramic capacitors are advised for high frequency. So ceramic capacitors preferred. Then the trace, your wire, the trace width should be large to reduce the impedance. See the R value equal to rho L divided by A. A is cross-sectional area. So A should be large, but the thickness is fixed. So you need to increase your width. Then you can lower your impedance of your trace, your wire. And the digital signal, clock on-off switch, should be shielded because they will create electromagnetic interference to your circuit, on-off. Also, your bias. So we have 5-volt bias to the accelerometer, but we have 3.3 volt bias to your AD7887. In order to decrease the variation, you can use a simple op amp. Use this voltage divider. So the output equal this one equal this one. So 5 volt times 5.111K plus 10K divided by 10K, you can get 3.3 volt output. Do you understand? Okay. So let's continue to next lecture. Load cell. Because we have sensor, usually pressure sensor to measure the pressure, or force sensor. I apply a force to say this one, the robotic hand. We have a tomato. So I want to feel the tomato. Then we need to have tactile sensor means touch sensor. Touch sensor. Tactile sensor. Contact. No contact. Contact. Okay, touch. Then we need to have tactile array sensor. So we have very small area contact. We have large area contact. So we need array of sensors to know what's the contact area between the robotic hand and the tomato. So we need tactile sensor. But also we need force torque sensor, because the robot, he may squeeze the tomato and damage the tomato. Because robot can be used to select good tomato and bad tomato, quality A tomato, quality B tomato, quality C tomato. So when the robot touch the tomato, the force cannot be too large, otherwise you are going to damage. So you need to touch sensor and force sensor, apply the right amount of force, then decide the quality of this tomato and put the tomato into the right container. So force sensor is important and torque sensor, because not only the force is important, also the torque you applied is important too. Moment. Then at the joint. So we have many joints here. The robotic hand. At the joint, we need torque sensor. Then we can apply the torque to grab the tomato. Okay, so all the touch sensor, tactile sensor is pressure sensor. and force torque sensor, and angle torque sensor. All these sensors, we can use capacitive sensor, the MEMS device. But for all the mechanical part, we need a circuit. So, and all these four sensors, they probably, most of them use Wheatstone bridge between the voltage and the conducting circuit. We need the Wheatstone bridge there. So now we are going to go to the four sensors. Example, this one, we have 4 anchors. We have 4 sensing beams. And each beam, we have strain gauge on the beams. Strain gauge can turn mechanical deformation into voltage signal, strain gauge. So suppose this is strain gauge. If you apply a force to the beam, the strain gauge, the resistance will be varied. So they are piezo resistors. Piezo means force. Resistor is R. So piezo resistors is force resistance converter. In electrical world, we have analog digital converter. But for mechanical world, we have force resistance converter. So this is force resistance converter, strain gauge. Then, okay, we just assemble them together. We put, okay, we have 3 strain gauge, and 1 strain gauge, delta R, and 2 small strain gauge, minus delta divided by 2, minus delta divided by 2 in series. So total is delta plus delta R. Here is minus delta R. So we create a strain gauge and 2 reference resistors. They are not on the sensing structure. They are outside the sensing structure. Here, outside. So they are constant. Here. So VDD, VSS. And this is a differential voltage output. So we can calculate V1 based on this configuration. Simple circuit. In the fabrication technology, we use this 1-poly 6 metal fabrication process. Metal 1 to metal 6. And we have poly, this is poly layer. And see, after CMOS process, for the circuit part, you can get a chip like this. After CMOS, the transistor, but the CMOS part are protected by the amorphous material, oxide or PSG, some oxide material. But in order to make the sensing material structure, we need to remove the oxide. We need to remove the oxide here. So yeah, this is a protection area. And we remove the protection material here. Then we can use the plasma to remove the oxide. Then after that, we can use agent to remove the silicon here to free up the sensing structure. Okay, this is a simple introduction of this fabrication process, the layout. Now, the key is the Wheatstone bridge for the sensing. For Wheatstone bridge, okay, this one are all the initial resistance, and RF is the resistance variation. So plus RF, minus RF, minus RF, plus RF. RS is the series resistance. You have wire. So RS here, what is RS?
The series resistance,
Where is it come from?
the wire.
The wire? Sometimes it's the wire, but sometimes we intentionally put this resistance here to compensate this Keystone bridge. Then you have V plus and V minus. So if you look at from the output, you have output resistance. If you look at to the input, you have input resistance, Re. Look to the input. So for Re, you have Rs. So to calculate Re, you can say you have a test Vt, and you measure the current It. Vt divided by It is your input resistance. You can do that. But you can look at this circuit. The input signal, Rs, we have Rs, two Rs, and we have Ro. So if you look inside, you have the Ro. So you can do the math. So, okay, please calculate the input resistance and output resistance of this circuit. For input resistance, you can put, say, V1 and you say I1 here. So you can do the math. You can get V1 divided by I1 is the input resistance. For output resistance, you can remove this one. Then you apply V out and there's current I out. So V out here and I out goes in. So you can use this circuit to get V out divided by I out is the R out, output resistance. So I have the result here, R in and R out. So please try to derive the input resistance and output resistance of this circuit. So for output resistance, this one is a short circuit. Just connect them together for output resistance. If you have no idea, you can ask the electrical major students, or you can see how they carry it out. I suppose they should be able to do this. Suppose. You turn off. VF max a lot, VF SOS a lot. You are going to see them for this week, next week. We are going to use the parameters for calculation. Okay, so we're going to know RF. Then for this simple circuit, the excitation voltage, V is the excitation to this Keystone bridge. suppose we have I1 flow, then this one, you will range 1, I2, range 2, I3, and go back here. So I1 in, I1 out. Okay? Then just because RF, you can just forget RF. RF is small compared to RO. Okay, forget RF. So I2, I3 should be the same. So I2, I3 equal to I1 divided by 2. Then the V out, this is VA, this is VB. So we define V out equal to VA minus VB. Then V out equal to VA minus VB. But VA, this one, equal to I1 RS. So VA, so this is the ground here. So the voltage potential is I1 RS plus I3 RO plus RF. And I3 is I1 divided by 2. So this is VA, this is VB, VB IS I1 RS plus RO minus RF times I2. I2 is I1 divided by 2. So you do the math, the result is I1 RS. Then, because I1 is the current, if you just look at V in I1, remember you did the input resistance calculation. So I1 is V in divided by R in, and R in is this number. You got this one in the previous page. Then substitute equation 3, this is equation 3 into equation 2, and solve for RF, you can get this one. So VA minus VB, you can get this expression. So RF equal RF here, RF equal to V out, V in here, and RO plus 2RS here. So you can, V in is your excitation voltage, and RF is the resistance change due to external force. Then V out is here. Okay, so any problem? Martin, any problem? Okay, so this is F. Then we have some definition. So V out divided by V in, we call this transfer ratio. Then we define this one. V out V in equal to 4 scale output span times, this is the spec. The load cell can, the maximum force you can apply to the load cell. And this one is the force you applied. So the force you applied divided by the 4 scale, the maximum force times 4 scale output span is V out divided by V in. So this is the relation given by the company. So equation 5, you can put this equation into this one, then you can get this one. So RF related to applied force. So if you know the force you applied, you can calculate the resistance change here. So, Leo, any problem? It's better after you go back home, after the class, before you go to sleep, just read this one, then derive the equations before you go to bed. Or now it's 4 p.m. and 5 p.m. you may go running, jogging. Or 4:30 p.m. you are going to do something else. If you spend 30 minutes, because now is the most valuable time, because your memory is still fresh. Then if you review all these slides very quick, maybe it only takes 30 minutes, 20 minutes. But if you don't do it, You want to do it, okay, tonight, maybe 1 a.m. So your memory is not fresh. It may take 1 hour to review all the data. But if you are, I have something more important to do. So I'll do this after 2 weeks. Then probably you don't remember anything. It may take you 3 hours, 4 hours in order to review the data. But still, if you don't want to do it, you want to do it before the final exam. But we don't have final exam. But if you suppose we have final exam, that's after 2 months. Totally, you have no idea about this. It may take 1 day, but still you cannot understand most of it. So I just try to encourage you to review the lecture just after the class. Just take 10 minutes, 20 minutes. You can go very quick. That's the most efficient way, I think, for learning. But if you can preview the data before you come to the class, the previous evening you go to iLearning 3.0, you can check the lecture, you can just go through it. You have some simple idea. Then when you sit here, it's review process 1. It's not the first. So if you come to the class, it's the review of what you learned last night. You are going to learn 100% of the lecture. But if you sit here, you don't do review, you come here, probably you can learn 70 or 80%. So the most efficient learning is preview, just 5 minutes, then listen to the lecture, review, 30 minutes, then I guess you are all set. Yeah, what, picture? Okay, we are going to the next slide. So, next week we are going to do the LT spice. So we will create this circuit in LT spice and run the simulation to see if we can get the result. So the result here, this is the load fail model. Because after 1 week or 2 weeks, the circuit is going to become complicated. You have Wheatstone bridge, you have buffer, you have the amplifier or ADC. And not only you have one Wheatstone bridge, you have 1, 2, 3, 4. You may have 4 Wheatstone bridge. It's complicated. But next week we are going to start from a simple Wheatstone bridge. You are going to learn from simple, then step by step, the circuit is going to become complicated. You will add more components into the LT spice. So it's going to be fun. Look forward to it. So any problem today? Martin, do you like me?
Yeah, sure.
Okay, I'll see you next week. Bye bye.